Okay, so you just watched a video on how to construct perpendicular bisectors of a segment. So this video is going to show you how to construct a perpendicular line to a segment, meaning not just down the middle like a bisector, but a line that just is perpendicular. It doesn't have to be down the middle. Okay, so this construction will come in handy. Make sure that you take some notes on how to construct a perpendicular line to a segment. So to do this, I'm going to start with that perpendicular bisector construction that we've already gone over, and you should be getting pretty efficient at. To construct the perpendicular bisector, making a 90-degree angle and going right down the middle of this segment, we take our compass tool, which makes a circle. We center it at an endpoint. I'm just going to go out to the other endpoint for my radius. That guarantees me two congruent radii, two congruent circles. So then the whole construction is that the perpendicular bisector contains these 2 points, right? And because that is the perpendicular bisector, points C and points D are going to be, the distance that D is from A is going to be the same as it is to B. And same thing for C, right? We can kind of, I hope you can imagine that rhombus here, that squished square, you know what I mean? Where all 4 of these distances here are the same. Okay, and notice that goes right down the middle here. So now my question is, how can we construct a line that's just perpendicular, like this line's perpendicular, but I don't want it to bisect. I just want it to go maybe right here, or just somewhere off of center. Okay, to do that, we're just going to change our radii. So I'm going to back up here. Here's our segment. I'm just going to construct a line that's perpendicular. Okay. So what I'm going to do is grab my compass or my circle tool here, and I'm going to create a circle centered at one of the endpoints, and I'm just going to make some radius. It doesn't matter where. Let's say, for instance, we have a point that's not on the segment or not on the line, like maybe this point C right here, and I want my perpendicular line to go through C. Okay, so to do that, all I'm going to do is grab my compass tool, my circle tool, center it at, say, A here, and I'm just going to go out to C, make a radius so that the circle contains that point that I want to go through. And then I'm going to do the exact same thing, center at B here, and go out to that same point. And notice what we have here is a reflection, right? We can imagine that if we had, say, well, let me talk about the perpendicular line first. Getting ahead of myself. I'm going to grab my line tool again, and I'm going to connect. Notice that point that we wanted to be on the perpendicular line is already an intersection point. And we have this other intersection point down here. So if I connect those two, I bet those are perpendicular. I'm going to grab my point tool, make the intersection point. And I'm just going to measure this angle to verify for myself that it is actually 90 degrees, and it is. So notice what we have here is a line that's perpendicular. It's 90 degrees to our line segment, and it's not going down the middle. And the trick to that is just using radii of circles that are different in size here. So if I were to move C like towards the middle, notice those 2 circles become congruent because we're using the same radius. But as I move away from center, the radii of the 2 circles definitely change. And that's how we construct a perpendicular line. So it's the same thing as a perpendicular bisector, it's just we don't want the radii to be the same. So for your notes here, I have the steps, and I'm going to just go through the steps here with this segment, and I'm going to grab my compass tool. Okay, so it says connect points with a segment if needed. So if we just had points, we would need to make the segment. Okay, but we already have the segment here, so we don't need to do one. Use an endpoint as a center of a circle and make a radius of your circle contain the given point, just like in my last example. If no point, then make radius any length. Well, on this one, we don't have another point that I want to make sure that we go through, so I'm just going to use this one. I need to make this tool here so that I can grab my center here. So now what it says is just make a radius. It doesn't matter. It depends where we want that perpendicular line to go. If we want it to go here, I just need to make sure that the radius that I pick is going to contain that point. So if I wanted a line to be perpendicular, say over here, I just need to make sure that I have a radius that's big enough to go over here. So maybe I'm going to use this. Okay, so I'm going to create a circle there. Now the next step says, using the other endpoint as a center of a circle, construct another circle that contains the given point, but there isn't one here. So if no point, make sure that the two circles intersect. Okay, so that's all that it says here. So just make sure that they intersect. So I'm going to center a circle at the other endpoint, and if I make this circle here, I just got to make sure that they intersect here. So if I do this circle that will get made here, you can kind of see where the intersection points will be. It'll be right here and right here, right? Maybe like right there and right here. Right, so that would be, if I connected those, that would be my perpendicular line. If I change my radius, it just changes my intersection points, say to here. That's kind of more of a bisector. Maybe if I didn't want that one, I'll make a bigger radius. And now, when I connect these 2 points with a line or a segment or a ray, that line is guaranteed to be perpendicular to our segment. So that is how we construct perpendicular lines. And all it has to do, really, why this is actually working, I'm going to go back to this GeoGebra construction here. So no matter what we do, as long as the two circles intersect, we'll get a perpendicular line, because, let's use some logic here. I'm going to grab my segment tool to show some radii, and maybe I'll make these radii red. So, I got my son back here, he's making some noise, so hopefully that's not annoying in the video. So to show equal length here, look at this left circle, circle A. So we label circles by the label of the center point, so this is going to be circle A, because A is the center. If I make a radius A to C, then that radius has to be the same length as, say, this radius A to D, because C and D are both on the point. They have to be equidistant, right? Because they're both radii of the same circle. Now if you look at this circle, circle B here, excuse me, I'm going to pause this video. Okay, sorry about that, guys. I got rid of my son. He was a little moody for me. So anyways, back to the reason why this perpendicular line construction proof works. We've got two radii that are the same, these red ones. I'm going to make these other two radii a different color because they're a different length. Oops, I still want this red. So this radius, because this circle is smaller than circle A, circle B here is smaller, meaning the radii then have different lengths. So this radius is not of the same length or congruent to these radii, so I'll make them a different color. But we do know that BD is also the same length as BC. They're both radii of the same circle, right? And since B is equidistant from C and D, we know it's on the perpendicular bisector of this segment. And since A is equidistant from C and D, we know A is on the perpendicular bisector of this segment as well. So this segment's actually the perpendicular bisector of this segment CD, right? Using the perpendicular bisector theorem. So what we construct actually with this is a kite. And what a kite really is just a four-sided, or what we call a quadrilateral, that has two sides that are next to each other that are congruent, and then two other congruent sides, but they're not congruent to the other two. So not all four sides are the same, but we have two pairs of sides that are congruent, kind of like this picture here. So no matter what this looks like here, right, so as we change things, I've got two sides that are always going to be the same, and the other two sides that are always the same. Okay? We can maybe get an inverted kite. Maybe not. Not with this construction. Oh, there we go, excuse me. Here's an inverted kite. Still, it's a four-sided shape. Two sides are equal in length. These two sides are equal in length, but not equal to each other. This is called a concave kite because we have a side that looks like it got caved in, right? Like this side got caved in, like that. So this is an example of a kite, and this is what we construct every time that we follow our construction steps. We're always constructing this kite when we make perpendicular lines, right? These are equal in length. These are different but equal in length, and there's our kite that are always perpendicular to each other. And we know that this side's always going to get bisected. So there is why the perpendicular line construction always works. Good luck, guys.